Good morning to all of you. In previous sessions, we discussed properties of Z transform. We discussed four properties, that is linearity, time shifting, scaling in the Z domain, and time reversal property. So in today's session, we'll be discussing another property, that is differentiation in the Z domain, and we'll try to solve two examples in this session. Okay. So we will be discussing differentiation in the Z domain. Again, if x of n, that is discrete signal x of n, has the Z transform capital X of Z, then n into x of n has the Z transform minus Z derivative of x of z with respect to dz. Okay, so that is the differentiation in the Z domain property. So here this x of z has been differentiated with respect to z in the Z domain. Okay, so if we are provided with the discrete time signal x of n and we want to determine, if we know the Z transform of x of n, which is nothing but x of z, and if we want to determine the Z transform of n into x of n, then we can take the derivative of this x of z with respect to z and we can multiply it with minus z. Okay, and both of these Z transform will have the same ROC. Okay, both of these Z transform will have the same ROC. So we'll try to prove this property here. Okay. So for proof, again we know that the Z transform of x of n is simply represented as capital X of z, which is nothing but summation n is equals to minus infinity to infinity x of n into z to the power minus n. Okay, I will try to take the derivative of this x of z with respect to z. Okay, so here we differentiate x of z with respect to z. Okay, variable z. So the derivative will be represented as dx of z upon dz. Okay, is equals to, it is derivative of this complete term, that is summation n is equals to minus infinity to infinity x of n into z to the power minus n with respect to dz. Okay, so I will rewrite this last equation, that is derivative of x of z with dz is equals to derivative of what? Summation n is equals to minus infinity to infinity x of n into z to the power minus n with respect to dz. Okay, but here as the we are taking the derivative with respect to the variable z, so this summation n minus infinity to infinity x of n will be the constant here, right? So only we have to take the derivative of z to the power minus n. So we can take this summation n is equals to minus infinity to infinity, right? X of n outside of this derivative, so derivative of z to the power minus n with respect to dz. Okay, so what will the derivative of it? So it will be minus n just into z to the power minus n minus 1, right? As we know that the derivative of x with respect to x will be 1, right? Correct, because it will be x raised to the power 1 is there. So just for example, if you want to identify the derivative of x square, so it will be this power will come in the multiplication and will reduce the power of x by 1, so it will be x raised to the power 2 minus 1. Okay, so it will be simply 2x, right? So here also we have taken this power of x in multiplication 1, x raised to the power 1 minus 1 will be 0, so 1 into x raised to the power 0, x raised to the power 0 is again 1. Okay. So here similarly the derivative of z to the power minus n will be simply this x of n will be as it is. This will be minus n into z to the power minus n minus 1 will be there. Okay. So from here we can take this minus sign. Okay, minus sign outside of this. You can take this minus sign and z inverse outside this summation, right? So this negative sign and z inverse, if I'm taking outside summation, so inside summation n is equals to minus infinity to infinity, x of n will be there, right? So this n will be as it is, so we can represent it as n into x of n. Okay, it is n into x of n. So I have taken this negative sign outside summation. Okay, so minus z inverse I have written. So n into x of n as it is and multiplied by z to the power minus n will be as it is. Okay, so z inverse also I have taken outside summation. Okay. Now I can send this minus z inverse on left hand side. Okay, so if I am sending this minus z inverse on left hand side, so this is the value of what? Dx of z upon dz. Okay, so if I am sending this minus z inverse on left hand side, so what I will get? So I'll get this minus z simply, okay, because it will be 1 upon minus z inverse, so I will send this z inverse in numerator, so it will be z simply. Okay, so minus z derivative of x of z upon dz, which is equals to simply summation n is equals to minus infinity to infinity n into x of n into z to the power minus n. Okay, so here we are identifying the z transform of this n into x of n. Okay, because this is nothing but the z transform formula, right? N is equals to minus infinity to infinity. In place of x of n, there is n into x of n. Okay, so we are taking the z transform of n into x of n. So its z transform is minus z derivative of x of z with respect to dz. That means n into x of n is the z transform what? Minus z derivative of x of z with respect to dz. Okay. So again, these both z transform has the same ROC. Okay. So let's consider that both transforms have the same ROC. Okay. So this is how you can apply differentiation in the z domain to determine the z transform of n into x of n. So let's try to solve one example here. So here again we have to determine the z transform of x of n is equals to n into e to the power n u of n. So initially we will try to identify the z transform of a to the power n u of n, and then by using the differentiation in the z domain property we can identify the z transform of n into a to the power n u of n. Okay. So initially find the z transform of e to the power n u of n. Okay. So the z transform of a to the power n u of n can be written as summation n is equals to minus infinity to infinity. Again, x of n into z to the power n will be the formula for z transform. Okay. The formula for z transform x of z is equals to that n is equals to minus infinity to infinity x of n into z to the power minus n. But in place of x of n, there is value a to the power n u of n. Okay, a to the power n u of n into z to the power minus n will be as it is. Okay, so again this u of n will be 0 for negative values of n and 1 for positive values of n, so I can modify it as n is equals to 0 to infinity a to the power n u of n will be 1 for these values, right? Z to the power minus n. Okay, so here again I can write it down as n is equals to 0 to infinity. So I take this n common, so it will be a into z to the power minus 1 raised to the power n. So again by using infinite geometric series, that is n is equals to 0 to infinity As in this, n is equals to 0 to infinity, a to the power n is equals to 1 upon 1 minus a, provided mod a less than 1. Okay, so here this z transform a to the power n u of n will be simply what? So it will be 1 upon 1 minus a z inverse. So we provided mod a z inverse should be less than 1. So its ROC will be mod z greater than a. Okay, mod z greater than a will be its ROC. So here we are determining the z transform of a to the power n u of n. It is 1 upon 1 minus a z inverse. Okay, so now we'll use this differentiation in the z domain property. Okay, so a to the power n u of n, we determine its z transform 1 upon 1 minus a z inverse with ROC mod z greater than a. So by using now differentiation in the z domain property, okay, we will determine n into a to the power n u of n's z transform. Okay, so as per this differentiation in z domain property, n into this will be minus z into derivative of that. Okay, so by using differentiation in z domain property, is a transform of n into a to the power n u of n, okay, will be simply minus z into derivative of this 1 upon 1 minus a z inverse with respect to dz, right? So if I'm taking the derivative of this term, so we know that the derivative of 1 upon a is what? It will be, because this is nothing but a inverse, so it will be minus a raised to the power minus 2, right? Derivative of 1 upon a is, right? So similarly you can identify the derivative of this 1 upon 1 minus a z inverse, so it will be 1 upon 1 minus a z inverse whole square. Okay, and you have to take the derivative of this 1 minus a z inverse in numerator, so the derivative of 1 is 0 and the derivative of a z inverse is simply, so this negative sign will come, z raised to the power minus 1 will come in the multiplication of it, so minus 1 will be in multiplication, so it will be a z raised to the power minus 1 minus 1, so it will be z to the power minus 2 will be there. So its derivative I will directly write here, so it will be simply minus a z to the power minus 2 whole upon 1 minus a z inverse whole square, right? So again this I can multiply z with z raised to the power minus 2, which will be simply z inverse, right? This minus minus will be plus, so it will be a z inverse whole upon 1 minus a z inverse square, right? So this is the required z transform of n into a to the power n u of n as per the differentiation property, and its ROC will be same as that of initial z transform, that is mod z greater than a. So this is the required z transform as per the differentiation property. Okay, so here initially we identified the z transform of a to the power n u of n. Okay, so a to the power n into u of n into z to the power minus n. So we have modified these limits. So we have taken the z transform of this a to the power n z to the power minus n. We have taken this n common. So as per infinite geometric series, we can write 1 upon 1 minus a z inverse provided a z inverse less than 1. So here mod z is greater than a. Then we have differentiated this z transform and multiplied it with minus z to get the say transform of n into a to the power n u of n by using the differentiation property. Okay, so the derivative of this 1 upon 1 minus az inverse is minus az to the power minus 2 1 upon 1 minus az inverse whole square. Right. So we'll try to solve one more problem here. Right. So here we have to determine the signal x of n. Okay, here the transform of x of n is given. Okay, so the say transform of x of n is x of z and it is log of 1 plus az inverse. Okay, and its ROC is mod z is greater than a. Right. So we know that the derivative of log ax, okay, with respect to x, okay, is what? 1 upon ax, 1 upon ax, and the derivative of ax is multiplication is simply a. Right. So that is the derivative of log ax. Okay, so here we have this x of z. Okay, so the given x of z is log of 1 plus az inverse. Okay, we know that we want to determine x of n here. Okay, and we know that the as per the differentiation in z domain property, if x of n is having z transform x of z, then n into x of n has the z transform minus z derivative of x of z with respect to dz. Okay, so initially we will take the derivative of this given x of z, right, and then from that derivative we want to relate this or identify this x of n. Okay, so we will differentiate x of z with respect to z. Okay, so what we will get? So we'll identify derivative of x of z with respect to dz. So its derivative will be 1 upon 1 plus az inverse, right? 1 upon 1 plus az inverse, and then we'll take the derivative of 1 plus az inverse in the numerator. So the derivative of 1 will be 0 and derivative of az inverse will be minus az to the power minus 2. Right. So from this z raised to power minus 2, we will send one z inverse on left hand side as well as this negative sign on left hand side. Okay. So reason for that is we need minus z derivative of x of z dz on left hand side. Okay. So if I'm sending minus sign and one z inverse on left hand side, so I'll get minus z derivative of x of z with dz is equals to, here I will get a z inverse whole upon 1 plus a z inverse. Right. And here this ROC will be same, that is mod z greater than a. Okay. So here what we have, this minus z derivative of x of z with respect to dz, and on the right hand side we have this a z inverse. Okay, I'll write this a z inverse, right, in bracket 1 upon 1 minus, not 1 minus, 1 plus az inverse, 1 plus az inverse. Okay, so this thing we have now. We'll try to identify the inverse z transform, because we are interested in identifying the signal x of n here, so we have to take the inverse z transform of this term, right? And this z inverse is nothing but the unit delay in that identified inverse z transform, right? but we are not seeing the methods of identifying the inverse Z transform. There are different methods of identifying inverse Z transform, that is Cauchy residue method. Then there is partial expansion method, there is long division method, okay, table loop method. So these are the methods for identifying the inverse Z transform. But we know that this term, that is, here I will write this term 1 upon 1 plus AZ inverse, okay, I can write it down as 1 upon 1 minus AZ inverse, okay. So we have just seen here the Z transform of a to the power n u of n. So what was that? Z transform of a to the power n u of n is 1 upon 1 minus AZ inverse, okay. So the Z transform of what? A to the power n u of n, we have just identified in the previous problem. It was 1 upon 1 minus AZ inverse, okay. So what is the difference between these two terms? So here it is minus a and here it is e. So the inverse Z transform, okay. So if I'm taking the inverse Z transform of it, okay, so then its inverse Z transform will be simply minus a to the power n into u of n, okay, because in place of a here, right, it is minus a in this case, right. So again, if I want to identify the Z transform of this minus a to the power n u of n, so here the formula will be n is equals to minus infinity to infinity minus a to the power n into u of n into z to the power minus n, okay. Here you can modify the limits as summation n is equals to 0 to infinity, so you can take minus a, right, into this z inverse I will keep, right, plus the power n, okay, and I have taken common. Minus a to the power u of n is 1 for these values, so it will be simply 1 upon 1 minus a z inverse, right. So therefore the inverse Z transform of this 1 upon 1 minus a z inverse is minus a to the power n u of n, correct, okay. So here now I will write this term on, basically simply I can take it as what, here a z inverse 1 upon 1 minus a z inverse, right. So if I'm determining the Z transform of it, right, sorry, inverse Z transform of it, because Z transform is the reversible process. So this A I will keep as it is, right, or simply I'll keep this A as it is, uh, and this Z inverse, okay, I will not write initially Z inverse, but the inverse Z transform of this 1 upon 1 minus a Z inverse is what? Minus a raised to the power n into u of n, right, right, minus what, minus a to the power n into u of n. But in multiplication there is z inverse. Z inverse means it is unit delay, okay, unit delay. If I'm providing unit delay in this signal, if I'm multiplying it with z inverse, so it will be a to the power minus a to the power n minus 1 u of n minus 1 will be there, okay. So this will be the signal, that is a, okay. So this a minus a to the power n minus 1 u of n minus 1, okay. So this is having the Z transform, this is this particular term, that is a Z inverse 1 upon 1 plus, I'll write 1 plus a Z inverse, okay. So that is nothing but this a minus a to the power n minus 1 u of n minus 1 is nothing but this minus z dx of z upon dz. Okay, but we know that this minus z dx of z upon dz is nothing but, so it is obtained from the z transform n into x of n. Okay, correct. So we can equate here this n into x of n is equals to, so this in place of n into x of n there is term a into minus a to the power n minus 1 u of n minus 1. Okay, so this n into x of n is equals to a into direct minus a to the power n minus 1, correct, into u of n minus 1, and we are interested in identifying x of n. So therefore x of n is equals to, I'll send this n on the right hand side, so it will be a minus a to the power n minus 1. Okay, so upon n into u of n minus 1. Okay, so this is the required x of n that we are identified from the given x of z. Okay, so what we have done here, we initially taken the derivative of this given x of z, right? So this is the derivative, right? We have modified that derivative so that it should relate to the differentiation in the z domain property. So I have modified it. We have taken the inverse z transform of this. Okay, so this inverse z transforming minus a to the power n into u of n. Okay, then we have multiplied or delayed it by 1 unit in time, so it is minus a to the power n minus 1 u of n minus 1. And then as per the differentiation in z domain property, n into x of n is minus z x of z upon dz. So we have equated these two terms, and from that we identified the value of x of n. So it comes to a into minus a to the power n minus 1 upon n into u of n minus 1. So in next session we'll discuss another property of Z transform, that is convolution property of Z transform. Okay. So thank you for joining this session.